Our next unit we're going to start into here is a unit on exponential growth, and we'll get into some logarithm models, things like that here. But today, we're just going to begin with looking at this concept of exponential growth. And a kind of definition there that you can use is something is said to be growing exponentially if you are multiplying by a value repeatedly, because that's the definition of an exponent. An exponent is multiplying a value over and over and over again. And the most common case where you're going to see exponential growth is going to be things where you have money involved. And so anywhere where you're talking about interest, something like that is going to be an exponential growth model. Anytime you use a term such as doubling, tripling, you're talking about an exponential growth model. Because when you're talking about something doubling, you're talking about something multiplying by 2 over and over and over again. And so therefore, that's repeated multiplication. That becomes exponential growth. So our first model here we're going to look at is the exponential growth model for situations where you have a change in a rate, involving a rate, such which would be a percent type of change, which most things you would hear about would talk about they're growing at a certain rate. And so this would be the model we would use for that. A equals P times 1 plus R to the T. A represents the new amount. So that's what you're finding. You want to know how much money is in my bank account after so many days. That's what you're going to find the A amount. P is the principal or the original amount. That's the amount you started with. What did I invest originally? What value are we working on a change for? R is a growth rate. That would be the percent you're changing by, and we always use it as a decimal. So therefore, if you were using 3.5% change, you would plug in 0.035 because we never use the actual percent. We always change it to a decimal when calculating. And T would be time. And for most everything we're going to do today, time will be measured in years. Also, that little section, the 1 plus R, gets its own special name. And that section is called the growth factor. And that's a big concept for what we're going to do here with exponential growth, is answering the question, why is it plus 1? Why don't you just multiply by the percent? And the answer to that is, when I'm looking at a percent change, for example, if I have a bank account paying me 5% interest, well, I could multiply by 0.05, and that would figure out how much the bank is going to pay me in interest that year. However, we don't want to know how much interest we're earning. We're looking for A, which is the new amount. That's the amount in your account after they've paid you interest. So therefore, we have to add the interest on to what is already there. And so that's why we multiply by 1, because multiplying by 1 maintains what is already there plus the new percentage. So that's why it's 1 plus R. Let's apply that model. And we're going to apply that model in a situation of population. Now, this is completely made up. The population of Chatfield, I have no idea what percent it traditionally grows at, but I just made up 3%. And we're going to say the population of Chatfield is growing at a rate of 3% per year. If the current population is 2,793 people, we need to write a growth model for the population of Chatfield at any point in the future. So to do that, we look at our original model. A equals P times 1 plus R to the T. And we're going to rewrite that with the information we know. We don't know A, so we're going to leave that as A. And we know the original amount is there are currently 2,793 people in Chatfield. Our rate is 3%, and we don't know the time. So this equation here, A equals 2,793 times 1 plus 0.03 to the T, is the model we would use to find the population of Chatfield at any time in the future. So if we would look at the second question here, how many people would you expect to live in Chatfield in 15 years? Well, that says use this exact same model, 2,793 times 1.03, except now we know the time. It's saying how many people will be here in 15 years. So if you plug that into your calculator and do 2,793 times 1.03 to the 15th, you get a population of 4,351.4, and because they're people, we're not going to cut them in parts, and we're going to call that 4,351. So this is an example of an exponential growth model. A mistake people often make in situations like this is they will take 3% of 2,793, and that's 83.79, so that would round to 84. They make the mistake of saying, well, 84 people, there will be 84 more people each year. That's not the case, because after you've added those 84 people, you're going to take 3% of that new number to figure out the second year, and the third year, and the fourth year. So it does not grow by a constant number of people, it's growing by a constant rate. So let's quickly look at one financial example here, because this is where most people see the direct connection to this in their real life. Is exponential growth involving money and interest is a very, very common place to see this. So we look at our formula. A equals P times 1 plus R to the T power. There's our model that we're going to use to calculate the amount of money in our account after a certain amount of time, and that time being years. We can figure out how much money will be in Aaron's account after a certain number of years. So if I wanted to figure out these questions at the bottom, for 10 years, we would take $1,400 times 1.045 to the 10th power. For 20 years, we take $1,400 times 1.045 to the 20th. And finally, for 50 years, it's 1,400 times 1.045 to the 50th power. All right, so after a little bit of calculation here, you can see the way stuff grows exponentially creates a large value of growth in a fairly short period of time. $2,174.16 would be in her account after 10 years. So in 10 years, she earned $774 for doing nothing other than simply leaving her money there. After 20 years, that account is worth $3,376.40. And so now you look, during the first 10 years, she went from $1,400 to $2,100. That's a gain of $700. Over the next 10 years, she gained $1,200 because the money is growing exponentially. You're earning interest upon the interest you've already been paid. And so our last value here, if she would leave that money in there for 50 years, that $1,400 turns into $12,645.69. So this is how interest is calculated. There are a few more complex things that we'll talk about later, but this is the basics of exponential growth. We take a percent change, we plug it in to our formula, plug in the number of years, and that will tell you how much money you have in an account, how much population there is in an area. Anything you can look at that changes by a percent can be done in this way.